Welcome, everyone. In this lesson, we're going to be looking at the idea of differentiability and continuity. So we're going to be kind of two related, sort of related concepts. And we're going to start off with the idea of differentiability, and we're going to see what that means graphically. So let's start off with our definition. So here we're defining what it means for a function to be differentiable at a point x. So we're defining what it means to be differentiable. And it basically means we have that limit definition that we've looked at before. That limit exists. So a function is said to be differentiable at x if that limit, as h goes to 0, f of x plus h minus f of x all over h, that limit definition of derivative, if that limit exists. And we know that sometimes with limits don't always exist, so we can run into trouble. And when that happens, we say that our function is non-differentiable. So our function is non-differentiable at some x value, x equal to a, if this limit does not exist. So there might be some x values floating around out there for our function where if we plug in the x value, then we run into trouble when trying to calculate this limit. And that can happen. So we're defining what it means to be non-differentiable here. All right, so graphically, what would that look like? And that's what we're going to investigate over the first example here. And so the way to kind of think about differentiability, kind of more of the intuitive graphical idea, is that differentiability gives us a way to sort of measure the smoothness of our curve. So it tells us, we're looking for, if we run into places where our function has an abrupt change, then we might have an issue with the derivative. And so a function is differentiable provided its graph does not have any abrupt changes or vertical tangent lines. And we're going to see what we mean by this. So for an abrupt change, or if you want to think of it like a sudden change in the slope, what can we have? Well, we can have just a jump or a break in the graph. Or another thing that can happen is there's a sudden change in slope. And this is just another thing that can happen. Maybe there's not a break or a hole or a jump in the graph, but maybe there's just a really sudden change in the slope. And we'll see examples of all of this. So let's actually start with the kind of the more obvious examples where there's a kind of a jump or a break in the graph. And so we're going to look at a bunch of graphical examples here, and each one of these, so there's 5 graphs here, and every single one of these has something going on at x equals 2 that makes this function non-differentiable. And so let's start with what I think are the kind of the more obvious ones. And that is these bottom 3. So in this first one down here, what we're seeing is that right at x equals 2 there, if we read up, we see that there's kind of a jump in the graph. So here, there's a jump at x equals 2. If we go a little bit to the left of 2, we're down here. And then if we go a little bit to the right, we're way up there. So there's a jump in the graph. Same thing going on in this middle example, but this jump is even more drastic. So if we go a little bit to the left of x equals 2, our function's getting really big. It's going up to infinity. And then if we kind of look on the right side, same thing. It's going up to infinity. And so you can think of this as almost like an infinite jump. And so the left side's going way up, the right side's going way up, and then we're kind of jumping over that x equals 2. What's going on there? And then in the last one, this one isn't really a jump, but there's something missing at x equals 2. So if we look at x equals 2 here and we read up, there's just a hole in the graph. There's a point that's missing. So there's a hole at x equals 2. So what's going on with these three is these are cases where there's either a jump or a hole in the graph. And we're going to come back to this idea in a couple minutes because these are kind of special. So we're gonna kind of classify these three examples. There's something else going on here. Now let's look at the kind of the more subtle examples of non-differentiabilities, and that is the first two. So for these first two graphs, there's not really a jump or a hole. So when you're looking at this, there's no break in the graph. There's no point that's missing. There's no, infinite kind of jump like this where we have where we would have a vertical asymptote. But what's going on is in each of these there's really kind of a sudden change. There's a really drastic change in the slope of our curve. So in this first one, let's look at this first one. What's going on? Well, we're going to have, what we're seeing here is there's a really sudden change in the slope right here at x equals 2. And we call this kind of where we have this kind of sharp looking point here. Again, think of differentiability as kind of measuring the smoothness, the smoothness in some way of our curve. And so there's this kind of sharp-looking point, and we sometimes call that a cusp or a corner, something like that, where it looks like the graph comes to a point, or there's just a really sudden change in the slope. So what's going on is if we look a little bit to the right, or if we look a little bit to the left, let's start with the left side, and we want to think about the slope. Imagine kind of drawing in tangent lines. Well, once we get really close to 2, the tangent lines are all going to be pretty steep, but they're going to be positive. So we're going to have some positive slopes on this side. So they're getting more and more positive as we get close to 2. Now, if we go on the other side of 2 and we look at the other side, drawing tangent lines, each of these little tangent lines are going to be pointing down. And as we get closer and closer to 2, they're kind of pointing further down. So these are going to have negative slopes. And so what's going on as we get closer and closer to 2, one side of our graph wants to have these kind of largish positive slopes, and then the other side wants to have this kind of largish negative slopes. And so it's hard to reconcile, once we get exactly at that point. And so that's what we're seeing here is it kind of just comes to a point. And it's not kind of a gradual or a smooth transition. It's this abrupt kind of switch over. So we call that a cusp or a corner. something like that. And if we wanted to, it would be impossible to draw the tangent line at that curve, at that exact point, because if we're looking at it from the kind of the left side perspective, our tangent line would want to kind of look something like that. And if we were looking from the right side perspective, our tangent line would want to look something like that. And so it's impossible to actually draw one specific tangent line at that point. That's what makes it non-differentiable. Now, something else is happening over here in the second one. In the second one, our graph has what's called a vertical tangent line. So if we were looking right at x equals 2, what happens is our graph right at that point looks almost vertical. Now, it's not quite vertical because it passes the vertical line test, but right at that point, the tangent line, the direction where our curve is headed, is kind of straight up and down. So this is an example of what a vertical tangent line looks like. So we're having a vertical asymptote here at x, or a vertical tangent line here at x equals 2. And so our tangent line wants to, right at that point, right at this point here, our tangent line wants to be vertical. And so a vertical tangent line has an infinite slope. And infinity is not a number. So, there's really no way to, because infinity is not a number, there's no way we can kind of give a value to the derivative there. Our derivative kind of wants to go off to infinity. All right, so these are the kind of the different possibilities for where our function has a non-differentiable point. We could either have kind of this really sudden kind of corner, or kind of a drastic change in the slope, not a nice gradual rounded change. We could have this vertical tangent line where our graph just momentarily it's looking vertical, and then it might continue on its way. So there are those things that have to deal with the slope, but then there's these other cases where there's just like a clean break in the graph, or there's a kind of a piece that's missing. And so it's these last two. These ones are related to the idea of continuity. And that's going to be our next definition. So a function is continuous at x equals a if this statement holds. So the limit of f of x as x approaches a is equal to the function value at a. And really what this limit definition is saying, if we want to think of it graphically, is a function is continuous provided the graph does not have any breaks or gaps. So really, we're looking, does our graph have any, jumps or holes in it? And another way to think of continuity is when you draw the graph, or if you want to trace over the graph, you should be able to kind of draw it without ever taking your pen off the page. It's kind of the intuitive idea of continuity. When we draw the graph, we can just do it in one swoop. So let's just go back. And that's what we're really seeing in these last three examples is in the first two, these are all continuous. Because if I start on one side of the graph here, and I can trace it over, and I never have to take my pen off the page. Same thing over here. If I start on one side, I can just trace it over, and I'm all good. I never have to kind of lift my pen up pick it up, put it down somewhere else, and then continue on. But that's not the case with these last two, or these last three. For this first one, I'm good here. This is all good. But now I have to take my pen off the page, put it back down up here, and then continue on. Ooh. Can trace better than that. There we go. And then I draw it. But right at x equals 2 here, there's kind of this jump. And when I'm literally tracing over, I have to take my pen off the page to make that jump. Same thing with this infinite. I'm good all the way through here, but then eventually I got to pick it up, put it down, and then continue on with the other side. Same deal with this this hole in the graph. I gotta jump over it. So I'm good tracing along here, but then I get to that point and I gotta stop, take my pen off the page. I can't draw over that hole, and then I can continue on. So what's going on is these first two examples, these are all non-differentiable but continuous. And these last three, where there actually is a kind of a break or a jump or a hole in the graph, these are all discontinuous. At x equals 2. So I should say, yeah, they have a discontinuity at x equals 2. All right, so we can kind of check. We're going to see how to actually check whether a function is continuous or not using this limit definition. And so what this says is that the limit of f of x as x gets close to a is equal to f of a. And really what this says, if we want to think about what does the limit say? Well, the limit talks about what happens near x equals a. So that's what the limit does. The limit describes the behavior of our function near x equals a. Well, what does f of a describe? Well, that describes the behavior of our function directly at x equals a. And so what continuity is really telling us is that what's going on right around x equals a, the left, a little bit to the left, a little bit to the right, if we kind of move away, the behavior near x equals a matches up nicely, matches up perfectly with what's going on directly at x equals a. So they all kind of match up and end up equaling each other. So that's really what this idea of continuity does, is it says, let's look around x equals a. Let's look directly at x equals a. And if our function's continuous, those two different behaviors are going to be equal to each other. So let's try this out. So in example 1, and I think we're just going to do part of these and then we'll finish up the rest in class. So let's maybe do, well, let's see how far we get. So let's start with the first one. That's a good one to start with. And let's determine whether this first function here is continuous at x equals 2. And we're going to use our limit definition of continuity to figure this out. All right, so the way we want to do this is we're going to kind of calculate 3 different things. So the first thing we're going to look at is our left-hand limit for our function. Then we're going to look at the right-hand limit. And then we're going to look at our function value. And what has to happen for continuity is the left side has to match up with the right side, and then they both have to match up with what's going on right at x equals 2. All right, so let's see what the left-hand limit is. So if we go to our graph, this is where, again, kind of imagine we're going to be on the left side. We're going to be getting closer and closer to x equals 2 from the left. So imagine being up on the curve and just kind of walking along the curve. And it looks like we're getting closer and closer to this point right here, which has a y-coordinate of 1. So the left-hand limit would be 1. Now, if we want to do the right-hand limit, x approaches 2 from the right, same deal. We're going to approach from this side. Imagine just kind of walking along the curve, and we want to know, well, where does it look like you're headed? And it looks like we're headed right to this point right here, so the same y value, which is 1. All right, so far so good. The two sides match up nicely, so the left side and the right side matches up nicely, but if we go to actually look at our function value, so now we want to know our function value, what's going on right at x equals 2, well, this is where we run into a problem, because if we look at x equals 2, this is not the point we're going to use. This is the point we're going to use, way up here. And the y value for this point is 3. So the function value at 2 is actually 3. And so this is where why we run into trouble, is because, yeah, the left and right side match up, but our function value doesn't match up. And so because these three values are different, these are not all equal, that means we're discontinuous. We have a discontinuity. We're not continuous at x equals 2. So that's really how we're going to check for continuity, is we're going to calculate these three gadgets, the left-hand limit, the right-hand limit, and then what's going on right at the function, and all three of these have to be equal in order for it to be continuous. All right, so we're going to stop there, and we'll try the next few here in class. So we'll see you then. Bye-bye.